Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
All right.
We're back.
We're back.
Look,
It's been a few weeks.
we're back. I know. It's amazing. I can't believe it. But look, my computer's like,
And why
it's
does our
like-
why does our green screen look weird?
It's phasing.
It's phasing.
You know, like
Don't like it.
it's like what was the Vision from the Marvel there? I'm rambling. The oh my gosh, where did it come from? The Age of Ultron.
Oh.
The Avengers movies.
Yeah.
The
I
guy, he
remember
like
that.
phases. He like turns invisible
Oh,
and
yeah.
goes through people and does a
that's
crazy
right.
thing.
Vision can do that.
Yeah, Vision. That's Vision. Did I say Vision?
Yeah,
What did I
you
say?
said
Yeah.
vision, but you may have said vision in the context of having a vision.
Oh, you know why I picked the wrong? I didn't pick the color green. That's what it was.
I'm like, that's better.
There we go.
This looks so much better.
I was
I'm like,
filibustering until I figured out what I did. I did
Yeah.
it wrong. You can tell it's been a while since we've been here, like
it's all good.
doing our thing. It's only been 105 million episodes. We're like 112 now, or 110. I don't even know. It's a lot.
It's a lot.
It's a big
good.
number.
It is a big number.
I can't believe it. Keep happening.
Oh, that's good.
I know.
Well, welcome everybody to another episode of Ask Us Anything about electrochemistry. I'm excited to be back. Are you?
I'm very excited to be back. I'm so excited. And I don't know what else. I don't know. I thought I'd be able to keep that going. I can't.
Oh no,
I'm
it's
too
all
old
good.
and jaded. No, I'm not actually excited. I'm not.
That's all good.
I am excited. And
awesome.
we're so excited that there was a question like 2 days ago that I saved from Reddick. And Reddick asked, can you explain mercury oxide calibration method? No. Yeah, we can.
Okay.
I'm in a weird mood. All right.
You're excited. You're
I
excited to
am.
be back.
I
This is how you express excitement.
It's a very
Partially.
weird way to express excitement, but why is, you can tell I also haven't used this before either.
Oh, try the make sure that your PowerPoint is up, like fully expanded, not
was it?
minimized.
Yeah.
That's-
Man.
It's
really
been a
has,
while.
It has been a minute.
We're a little rusty, but we're okay.
here.
Let's go back to this view. Here we go.
Okay. So mercury oxide calibration. Okay, so broadly speaking, the calibration of any reference electrode is the same whether it's mercury oxide or calomel or anything else. Basically, what you're going to do is you're going to take your mercury oxide reference electrode. Okay, it might look something like this. There might be a pin at the top, and maybe there's a frit in here. And what the other part of this procedure is that it necessitates the need for another reference electrode. So often we recommend you have what's sort of known as a master reference electrode that you keep in your lab that you never test. So this is your, let's say, HGO reference electrode, right? You're going to have some kind of reference electrode that's your master. So this can be another HGO. Sometimes that's hard to do because HGO is kind of expensive, right? So this might be, this could be HGO, it could be AgCl, it could be calomel. Okay, it could be anything, right? Now I understand the scariness of, let's just say, combining mercury oxide with something like silver chloride, because mercury oxide works with alkaline, right, typically, and something like AgCl you don't want to use with alkaline too much. So one of the things you could do, for example, is use like a very low concentration, so something like, let's just say 0.05 molar KOH, If your master reference electrode, for instance, is AgCl or calomel, this won't be too badly. You don't want to use like strong base with those kinds of reference electrodes, but very weak alkaline, roughly speaking, it won't be too big of a deal. So basically all you're doing is you're putting these in solution and you're connecting a voltmeter between the two and reading OCP. That's really it. You're looking for two primary things, right? You're looking for, this could be a potentiostat or just a voltmeter, literally just a voltmeter, a multimeter. You're looking for potential over time, and you're looking for two things. So whatever this potential is, so if these two electrodes are the same, HGO, your potential should be zero. Like roughly speaking, your potential over time will be zero. If it's not, if it's calomel or something, then this, HGO is like 98 millivolts, calomel is 200 something, so your difference will be minus 100 something, whatever. You can do the math on this. I'm not going to waste time doing algebra. Suffice it to say, the number should be roughly equivalent to the difference between those two reference electrodes. And the other thing is you want it to be stable over time. That's right, inside. So the let's just say something like 5 to 10 minutes of measurement time. This shouldn't drift. Like if your OCP measurement is swimming around or constantly changing, or maybe it doubles back on itself and it's kind of everywhere. Something is off. There could be a blocked frit or a partially blocked frit. Something is sort of messy, right? You want it to be relatively stable, and you want to know hopefully that the value that you're getting makes sense based on the difference between those. That's really it. And the only other things that you could talk about calibrating per se would be the internal fill solution. So one of the things you can do is you can drain the internal fill solution and refill it. So this is normally something like around 4 molar KOH inside of the mercury oxide reference electrode. So sometimes you can drain the solution and then refill it with fresh solution. So that's one way to, like, it's not really calibration, it's just sort of maintenance. Sometimes if something gets contaminated or whatever, that's one thing you can try to do. But mainly speaking, this kind of an open circuit potential test is what you would do to sort of validate your reference electrode is functioning properly. I don't know if you have something to add. That's kind of it.
Yeah. Only thing I want to add is on the Pine Research website. I'm just going to share this quickly.
Yeah,
we have so if you just go to I was actually on it ahead of time. If you go to pineresearch.com, we have tools. There's reference electrode conversion. So this is it's just a very easy tool. Normally you would just type in what is the voltage and then 100 millivolts, and then you'd put versus what. And then in this case, it calculates what those values are. So this isn't designed necessarily for comparing reference electrodes, but it's very helpful when you want to compare just between two reference electrodes. So in your case, mercury oxide, and then it even has all the different like concentrations based on the inner fill solution. So this is just a helpful resource just by going to pineresearch.com and then tools reference electrode conversion. So that was my only thing I wanted to share or add to that comment. Otherwise, yeah, you're absolutely right.
Very good. Yeah, that's a good one.
Yeah.
Tiparudra has a question. Looks like you asked for some clarification.
Yeah, I just wanted
was asking about impedance for battery state of health analysis. You asked what you're talking about, and so follow-up was that how can EIS be used to predict battery state of health, for example, or by analyzing circuit parameters, which circuit parameter needs to be considered, RS, RCT, etc. There's no one answer to this question, but I can give you a few tidbits, I suppose. So first of all, when it comes to circuit parameters, you can certainly study things, I would say, somewhat broadly in terms of state of health. So resistances, certainly, capacitances as well, or CPE values. So for instance, a battery might have, again, I'll start to draw a little bit for you. So if your battery at time 0, perfect health, has a Nyquist plot. This is like, time or cycles equals 0. So it's this initial whatever, right? You might have something like, I don't know, this would be like the SEI, the first semicircle. This would be the anode. This would be the cathode. And then this would be mass transport, something like that. All right. And then let's say at time equals 1,000 cycles or whatever, right? What you might see is something like, there's bigger semicircles, right? I kind of drew it like crazy here.
Yeah.
But one of the kinds of things that you'll be able to do, right, is to say, R, this right here would be like RU. So you could look at, did that change uncompensated resistance? In all likelihood, it might not too much, but you could say how the RCTs for, SEI or anode or cathode, right? So any of these RCTs is less than the T equal 1,000 RCTs. So like the RCT got bigger. So if the resistance gets higher, the charge transfer resistance is higher, so the reaction is slower. It's worse. That's one way to look at the state of health, to say, sort of, broadly speaking, my battery is performing more poorly. Another thing would be the capacitance. You could say if you're fitting these with, RQs or RC, how does this C for each of these go up or down, right? The capacitance is the ability to store charge, basically, right? So if that decreases, that's bad. It's like it's the capacitance is less. It's not storing as much charge. It's that's its primary purpose as a battery. Okay, so those are some of the things that you'll do. The other kind of state of health analysis. So everything I just described is quantitative and also I don't know what the right word is. It's based in
Qualitative?
Well, the other one would be empirical as well.
Empirical.
I don't know what the
Okay.
opposite of empirical is, right? This one's like grounded in reality, theoretically, right? Like you're applying a model and you're saying, and you're observing changes in what are measured resistances associated with these processes. So it's like real. It's like real numbers. The other kind of state of health analysis, and I did some of this when I was a postdoc, is entirely empirical. And so it's what some people have done. I did some work on this when I was a postdoc, is you do impedance at various times or at various temperatures or at various states of charge, or various battery conditions and times. And you can correlate something with the battery. So for example, one of the things that I did, I can speak for this personally, and there's similarities in other folks in the field that I know that have done this kind of research. I put a battery at different temperatures, right? Because you can imagine when a battery is between, let's just say, like 20 and 80 or 100 degrees C, it's all right. Once it gets above like 140 C, you start to get to a danger zone. Thermal runaway is a problem, right? So what I wanted to see was, how do impedance results change? And I'm not even talking about RCT and capacitance. I'm talking about like the Z imaginary at 10 kilohertz, something that specific. But it's also like, what does that mean? It doesn't mean anything. So what I did was I took a bunch of impedance spectra at a bunch of different temperatures in an oven, right? I heat up the battery to 80 C and I take the impedance spectrum. I cool it down to 20 C and I take the impedance again. I heat it to 150 and I take the impedance spectra and see what it looks like. And what you find when you do that is that there is correlations that you can make between what the like Z imaginary is at a specific frequency and the temperature. And so, for example, one of the correlations that I found in my research, and others have done kind of similar stuff at times, was that I was able to make a plot that was something like some ridiculous thing, which was like temperature down here. So this is like, let's say 20 C, and this was like 160 C. I'm just making up these numbers. I'm not sure exactly what they are. And this would be like the minus Z imaginary at 10 kilohertz. So it's like, what does that even mean? Doesn't matter. Who cares? This is what you get. You get something like this. And it's like, I could either, it's like, maybe I could fit it to like, 1 over the square root of temp, like, minus Z is equal to, and it's like, well, what's the equation? It's entirely empirical is my point. But if I can fit this to an equation and it's predictable, and I can say, uh, I'm not going to do undo because I'll kill the whole thing. Minus Zi is equal to, like, let's just say, some constant A over the square root of temp plus a constant B, like whatever, like some equation, whatever, right? I can make something like this relatively reliably. Well, then what I can do is in the field, right? I can say, well, what's the temperature of my battery? Or if it's not temperature, I can infer like, well, at high temperature, the state of health is like bad because it's hot and it's not good, right? Okay, so you could look at it as state of health or temperature. Like, state of health is a term that doesn't really mean anything. It's very vague. It's like, what's the state of health of my battery? Is it healthy or not healthy? It's like, well, what does that mean? Is it overheating or not overheating? Is it overcharged or not overcharged? State of health is a kind of vague, nebulous term. So I looked at it in terms of temperature, for instance. And then again, one of the things you could do is say, at a very quick moment in time, I can just take a 10 kilohertz pulse. That's really easy, right? Get the minus Zi. It takes almost no time to do this. And I can say, okay, well, my Zi was here. And so within some reason, I can say, oh, it looks like my battery is somewhere between like 110 and 130 degrees C. Like, oh, it's overheating. So it's like, I can say like, well, I want my minus Zi at 10 kilohertz to be within this range so that my state of health is happy. Right. So that's one way, and that's entirely empirical. So that's another way that impedance is used for empirical state of health testing. That's just temperature. That's one aspect of state of health, but you can do it in terms of overcharge. You can say, oh, let's study the phase angle at a particular frequency, or a phase angle over a short range or something, at different states of charge, and use that as a diagnostic tool. So that if you see a phase angle or a Zi or a Zmax, whatever, later on in a certain range, you can infer, oh, it's overcharged. That's bad. Something like that. Okay. So that's another way that impedance is used for state of health monitoring. It's kind of cool, actually, because it's like, it's dangerous in some sense because using empirical relationships can break down because there's no theory behind it. It's like, just if this number happens, then this number means something. It's like, why? Well, we don't know. It doesn't matter. Right. So it works as long as it works. Right. And it might not work for every battery and every situation and every chemistry. There's things you have to be careful with these kinds of relationships. But if you can develop these that reliably work, they can be really useful for predictive power, I guess you'd say.
This is the difference between engineers and chemists.
Yes.
Just like, you get something that works, it's like no idea why. It's like, why does it work?
Don't ask questions.
Don't ask questions.
That's right. Yeah, you just multiply, you raise it to the 10th of a power, and then everything's great.
And everything's great.
Yeah, but why? I don't know. Who cares? It works. It makes this little squiggly curve. It looks nice.
Yeah.
Yeah, we don't ask why. We just ask if.
Yes.
If it works.
If it works.
That's right.
Looks like Subash has a question. Subash is asking, if we are giving positive potential in CV, in the CV graph, but the graph is showing negative window, how it is solved. So what I think you're trying to say is, like, if you're applying a positive potential, but you're getting, say, negative current, when you're talking about negative window, I think you're talking about getting negative current reduction reactions to occur even at a positive potential. How has that happened? So this often happens because our understanding and the relationship behind what a reference electrode is and the potential that you're making measurements with is somewhat convoluted. So what I'm sharing right now is it's just a little thing I did from a recent webinar series I did. But basically, with reference electrodes, we have the standard hydrogen electrode that's kind of the center. Everything is kind of based off of it. And in this particular example, I have two reactions. I have a reduction reaction. A plus an electron goes to B. It happens at a negative potential. And then I have C, oxidizes to D plus an electron at, say, 0.55 volts. Positive potential, oxidation reaction, just what we would normally observe. And it's relatively easy to say, okay, using an SHE, first off, it's theoretical, but even using an NHE isn't always practical. Silver chloride's a very good reference electrode. So if we employ a silver chloride reference electrode, we can measure the difference between, say, this oxidation reaction. It would report at 0.353 volts versus silver chloride. So when this reaction occurs in, say, a cyclic voltammogram, we would observe the peaks around 0.353 volts positive. And similarly, for this reduction reaction, we would observe the CV peaks around negative 0.867 volts versus silver chloride. So the reason I bring this up, this is relatively easy to understand, but the situation that you're referring to is the case where, let's say I have a special reference electrode, and that special magic reference electrode is at 0.9 volts versus SHE. Now, with this magic reference electrode, which is just based on a redox couple from the Nernst equation, you can make one. You would report in this specific situation that at a negative potential, you get a oxidation reaction, which we normally assign with positive current. So in your case, this is from a webinar I did a while ago. But clearly, you're talking about the situation where I think you have, positive potential but negative window. So let's see, positive potential. So you would be over here. You'd have a reference electrode here, but you're observing a reduction reaction in a positive, or you're getting a negative. Sorry, you're getting a reduction reaction to occur at positive potentials with respect to, say, this point here. And that's really the key. The key is to remember that these reference electrodes just measure relative positions, relative spots. So the position, even if it's a negative, I want to make sure I'm using the same words usually. Even if you are at a positive potential, you can have negative reduction reactions, because this reaction here would happen at like +3 volts versus my special reference electrode that's in this region. But I'd get a reduction reaction. I have negative current, even though the potential in my CV is positive. So that's how you need to think about it. These reference electrodes. It's to say two things. These reference electrodes are really, in a way, placeholders. They represent points where we measure things with respect to. But then it also means that just because the potential is negative or positive, it doesn't exactly mean that it's a reduction or an oxidation reaction. It all depends on where the reference electrode is. Now, I will say, in general, most of the time, a negative potential is associated with a reduction reaction, and a positive potential is associated with an oxidation reaction. But that is not necessarily the case, just based on how these scales work. So, Subhash, I hope that this is helpful, that it kind of provided a little bit of clarity. I think that's what you're asking. And of course, I would also mention, if you want to watch the entire webinar of what I was talking about earlier, it's all about the concept of the electrode potential. And it's currently available on our YouTube channel. You can just look at voltammetry series under live videos, live streams, and you could see it. You can see electrode potential, and you can watch it, and you'll hear me go over that part about reference electrode potential. So, Subhash, if you have any further questions, let us know. Okay, so
it's almost like you just did a whole webinar series on something like that.
I know. Yes. I did. For those who are watching, I did just finish a recent large webinar series on voltammetry, where I talk about the electrode potential, kinetics, mass transport, everything that you need to understand cyclic voltammetry. And then from those fundamentals, you can now understand how the cyclic voltammogram works, how the experiment works, what's actually happening, kind of on a practical and theoretical level. And then we even go into some higher level stuff with coupled chemical reactions, as well as what is it? Differential pulse voltammetry. So the pulse techniques is also a form of voltammetry that's valuable. So yeah. So those webinars, those episodes are available now on our YouTube channel. So definitely recommend watching them if you have a chance.
All 4 parts.
All 4 parts.
And you should watch both time slots in each part. If you really want to be, thorough, you'll watch the morning and the afternoon and each of them and see how much better you did it in the afternoon than it was in the morning.
Maybe. I feel like in one of them I did mess up a little bit more in the afternoon because I was like, I'm just tired. I already did this. It's the end. Whatever.
I always tend to feel when I do 2 time slots that my second one is better.
Oh yeah.
I don't know if that's true. It might not be. My like feeling is always that I did a better job in the second, because
yeah, you've done it at least.
I
one
did
more time.
But yeah, and it's like in the morning, in the first one, I'll like say something away and I'll be like, I don't like the way I said that. And then like in the second
and you'll fix it.
Second one, I kind of fix it.
Yeah.
But it's hard to like keep track of all the things you said either too, because I don't script everything. Like,
oh yeah, no, I mean, I don't script things either, which is, as I've thought about it, I was kind of like, I miss making just the regular YouTube videos because I'm able to like really craft and perfect them to a certain degree. I can adjust every frame and make it like really tight. But here, webinars can't do it, but they have their own special value, if you will, in their own right. Because to make a video that's super long and to cover all the content, it would take a very, very long time.
It would.
Not that that's a bad thing, but definitely takes a lot of time.
I like the webinars. I like the webinar format. It does take a long time to like get all the content ready, but
yes,
but I do like the webinar content, the webinar format, I should say.
Looks like Subhash found my answer satisfying, so you're welcome.
Yes,
you're welcome,
nice.
Subhash. All right, good.
So if there are more questions, feel free to type them in. I think there was a question on our YouTube channel like not too long ago about the Warburg, the finite Warburg elements. I think these tend to, I don't know, trip people up. They tend to get a little bit of confusion, I think. So while we have a chance here, while we wait for some more questions, I think what I'll do is I'll go through some slides from one of my webinars going through Warburg models. So I'll just stick to the finite Warburg models. And I think what I'll do is go through these while we wait for some more questions. Because these are things that people then, in my experience, if I can figure out how to work a computer this time. And I think these are things that people often get tripped up on, have a difficult time with. So let me try to go through this. So this is from my third of my 5-part webinar series, impedance webinar series. And I'll just go through this short part of it as a little free educational session, I suppose. This is on specific circuit elements. And so I've, at this point in the webinar, have already gone through infinite Warburg diffusional element. And so now we get into the finite ones. And again, this is just something that I've had a handful of questions on recently. So I'll kind of talk through it. So this is the Warburg diffusion, the finite. There's 2 types of finite Warburg. There's short and open. And so the first one is short. The difference between this and the sort of normal Warburg W that everyone thinks about with the 45-degree tail and low frequencies and Nyquist plots, for instance, is that this is no longer semi-infinite diffusion. So we have a fixed boundary length. So the sort of factor, the main factor of the Warburg element is that it's a semi-infinite diffusion layer thickness compared to the size of the electrode effectively. Or that diffusion goes basically infinitely into the bulk. So when we have diffusion, but it's through a fixed length, we have to use these finite Warburg elements. And so there's also, sometimes this is called absorbing. Short is the more common, I think, word that's used, but absorbing, Warburg absorbing is also used sometimes. And it's usually denoted with WS. And so this you can think about as diffusion basically through an interface of a fixed thickness. So there's an example I always like to give, which is a gas diffusion layer of a fuel cell. Okay, and so a fuel cell fundamentally is a bit of a mixture of a gas and a liquid phase system. You flow hydrogen on one side on the anode side and oxygen on the cathode side, and the gas diffuses through what's called a gas diffusion layer, GDL, and to a catalyst, which is usually something like platinum. And platinum both catalyzes the splitting of hydrogen into protons and electrons, as well as the oxygen reduction reaction into water, combining with electrons and protons through the membrane and through the circuit. Now, the diffusional part that we're concerned with here, this is like an SEM image of a cross section of a membrane electrode assembly. Okay, and so we have platinum. We have the membrane. The middle part is the membrane, and the platinum is right on the membrane. And behind the platinum is basically like a thin carbon paper. Okay, that is the gas diffusion layer, and that is effectively the diffusion length, the diffusion thickness where it's going through, that makes the Warburg finite applicable. And so we have oxygen flowing on the back side. It flows to the back of this carbon paper. It's porous and fixed, and it's like a few hundred microns in thickness, roughly speaking, right? And so the oxygen diffuses through that carbon paper layer, that gas diffusion layer, to the platinum, where it is able to be reacted and catalyzed. Either the oxygen side or the hydrogen side, both of them have this kind of phenomenon, okay? We just normally focus more on the oxygen side because it's the rate limiting step in a fuel cell. Now, mathematically, the impedance of a Warburg short has this kind of fun equation. So we have the first part of this, W over the square root of J omega, that is the mathematical impedance of a Warburg infinite. So the Warburg short adds this extra term, which is the hyperbolic tangent of another constant B times the square root of J omega. And B is this extra constant that takes form in the Warburg short, and Warburg open, the other, basically Warburg finites, which is defined as delta over the square root of D. So this is the diffusion coefficient, and this delta is the boundary layer thickness. Okay, so you can see, for instance, right away that if delta is infinity, B is infinity. So that's the case where I have an infinite boundary length, just like the Warburg infinite. And you can convince yourself that that makes sense, because if B is infinity, the hyperbolic tangent of infinity, for those who remember it's not really trigonometry, because hyperbolic tangents is like an exponential function, but let's just pretend it's math.
Well, yeah, I think it's still part of trigonometry, but it's like,
yeah,
it gets crazy.
Well, if you like math.
Yeah,
right?
if you like math.
The hyperbolic tangent of infinity is 1. Okay, so the moral of the story is that it's 1. Yes. So in other words, at infinity, the hyperbolic tangent term just kind of, it's unity, it goes away effectively, and the mathematical expression for the impedance simplifies to the infinite Warburg, which makes sense. It should. So mathematically, this is consistent. What is really fun to look at is when you solve analytically this expression here, it turns into this. So that's super fun. And if you're looking at this and you're scared, I understand. However, what we can do is do some simple limit observations of this really crazy equation. And the first is that at high frequency, what happens is this term here, this e to the 2b, you see there's a frequency in the in the exponent here. Okay. And so basically these terms go to 1. Like you can do L'Hopital's rule. I think it's L'Hopital's rule or Le Chatelier's, which I always mix those up. I think it's L'Hopital's rule. The limits basically of infinity over infinity goes to 1. So these terms go away. What you're left with is at high frequency, you have just these expressions, the W root 2 over 2 over root omega on both of these. That is an infinite Warburg. So at high frequencies, a finite Warburg just behaves like an infinite Warburg. At low frequencies, however, what we have is that this whole term just goes to 0. You can trust me. I promise that's what happens. And so this whole term, we have only a real component. And this whole term, if you do the math out at omega equals 0, this simplifies to W times B, which is a constant, right? Well, the impedance of a Warburg short at low frequency boils down to a constant real impedance with no imaginary impedance. That's just a resistor. So a resistor is an element with an impedance that's just a constant, right? So basically, another way to look at the Warburg finite is that it is something in between an infinite Warburg and a resistor. So you can kind of tether your understanding of the finite Warburg element to two other things that perhaps you might have a better grasp on, which is the infinite Warburg and a resistor. Hopefully those are things that you might have some experience with if the finite Warburg is making you confused, let's say. Graphically, what you see is something like this. It looks like a semicircle, but it has a 45-degree feature at the high frequencies because, again, at high frequency, the Warburg short acts like an infinite Warburg. So it starts off with this 45-degree kind of feature right here, right? But at low frequencies, as it goes along, it curls down towards the x-axis, and that's a pure resistor, where it would just basically be on the x-axis. It goes to a constant. Okay, and so graphically, what you get is that you go from 45 degrees down to a point on the x-axis. Visually, it just makes what looks like a semicircle. And the width of this semicircle is effectively W times B, something like that. And so that's kind of like, you can almost like, it's an odd phrasing, but it's almost like the resistance of that diffusion, like the charge transfer resistance almost of this Warburg short element is W times B. So that's one way to look at it. Okay. I'll go through this again. I think there might be another questions coming in here. That's fine. We'll get to those in just a moment. The other finite Warburg element is called, another example I have, one other example of the Warburg short, I talked about the gas diffusion layer, is a rotating disc electrodes. So this is just another example where you have a fixed boundary length. So when you rotate an electrode, you force solution towards the surface. That creates a fixed boundary length, again, for the finite Warburg short. And when you compare that to a stationary electrode, so there's just any electrode in solution, you have this infinite boundary length. You have the Warburg infinite, right? It grows over time. When you rotate your electrode, you force the solution towards the surface. As I said, that creates a fixed boundary length, okay, which allows you to use the Warburg short because this delta is some number. It's not infinity. This is the difference between natural diffusion versus forced convection. Okay, so this is just another example where you can manipulate your system to have a boundary layer that's fixed rather than infinite, especially in solution. Visually, this is just some data to prove to you that that's what happens when you increase the rotation rate. You see this Warburg short like I showed. You have that kind of lagging 45-degree feature. And then it starts to curl down. You get what looks like a semicircle. Okay. Now the second kind of finite Warburg element is called a Warburg open, also called a reflecting or a blocked boundary sometime, but WO Warburg open I think is the most common terminology you'll see. This one's a little harder to conceptualize, but it's one of the examples is in a battery. Oftentimes with lithium-ion batteries, what you have is this fixed length of diffusion within something like a cathode or an anode, but the boundary condition now is like solid and not absorbing, right? So it forms almost like a capacitor, which looks like this. That'll be relevant in a minute when I look at the mathematics, but you can see that with a battery electrode, there's a current collector, which is either usually copper or aluminum, and it's solid. So unlike the gas diffusion layer, where the oxygen kind of goes up to the carbon paper and then it goes through the carbon paper, here the lithium ions go up to the current collector, but they can't go through it. It's solid. It's a blocked solid boundary, reflecting boundary, whatever. And so you have this kind of diffusion up to a point almost, and then some sort of capacitance you can almost imagine. And that's what this looks like here. The graph, you can see that the line goes straight up on the Nyquist plot. That's what a capacitor looks like. Mathematically, again, we'll prove to you that it's mostly capacitive in nature as well, because now it's the same mathematics of as the short, but we have a hyperbolic cotangent instead of a hyperbolic tangent. Same constants, W and B, same situation where the hyperbolic cotangent of infinity is 1. So again, when the diffusion layer thickness goes to infinity, B goes to infinity, this term goes to unity and basically goes away. So it does, again, we can start with the same kind of crazy mathematics here. At high frequency, both of these terms go to unity. We have an infinite Warburg. So again, at high frequency, both finite Warburg elements, open and short, basically simplify to an infinite Warburg at the highest frequencies. Where this changes from the other one, though, however, is at low frequency, this first term goes away instead of the second term. And the second term simplifies to minus W over omega B. And so before, we had W times B in the first term, and that was a constant, that was a resistor. Now this, mathematically, what happens? Well, at low frequency, the impedance of a Warburg open is equivalent to no real components, only an imaginary component. There's a J here, right? And it's inversely proportionate to frequency. That's a capacitor. I've just described a capacitor. So again, we are thinking of this Warburg open as something like an element that's bound between two other things that you hopefully have some understanding of, which is an infinite Warburg and a capacitor. The other one is an infinite Warburg and a resistor. So these mathematically behave as almost like a hybrid element. Graphically, what we see is this, instead of curling down to make like a semicircle, it curls straight up, right? We have this 45-degree line, and we have what is effectively like a capacitance of B over W. So instead of a W times B resistance, we now have a effective capacitance, if you will, of this finite Warburg element. And so the other last thing I'll mention is that at times people have asked questions like, well, I tried to fit a Warburg open and a Warburg short. I'm not sure which one, is applicable. There's two ways to look at that. One is, what is your boundary condition? Is it a porous, absorbing short boundary? Or is it an open, blocked, solid, reflecting boundary? These are boundary conditions. That's another engineering kind of thing mathematically, but the boundary condition should impact which of the finite Warburg elements you would use. But then the other is that take impedance and look at it graphically. Because if the line goes straight up, it's a Warburg open. And if the line curls down to a semicircle, it's a Warburg short. They're pretty graphically different and distinct. So hopefully your data will show pretty clearly which one is most appropriate for your data, just graphically based on what it looks like. So if you tried to fit a Warburg short to this data, it won't fit very well. Like, it goes straight up and down, right? It won't really work. So I think that's kind of all I had on those. So I hope that might be helpful for anybody who is watching now or takes a look at this later. Again, that's just a question that I feel like I've gotten a handful of times. The Warburg short and Warburg open. So hopefully that kind of wraps those up a little bit for you. That's right from my webinar.
Yeah. All right. Yeah. No, very good. We do get a lot of questions about infinite, finite, Warburg, and the different things, and it is a confusing subject. So we got a couple questions that came in. Lev has a question. Lev is asking, can you use the Aftermath software to fit experimental CV data? Well, the answer is a little bit kind of yes and no. So I will show you. We have what I would say is cyclic voltammetry simulation data. So we can simulate cyclic voltammograms, and then you can adjust some of the parameters in your simulated voltammogram to match an experimental voltammogram. So here, actually, let me get rid of these. This is experimental CV data that I took. And what I can do, I'm in Aftermath Live. This is a web browser. We're in a web browser. And what I can do is I can take this voltammogram, I can pin it, and then when I open up, let's just open up a new CV simulation experiment, you'll notice that in the upper right-hand corner here, I have my voltammogram, kind of faded, very faded light red, light pinkish color. And what I can do is I can add in my experimental parameters for this experiment. So in this case, I went from 100 to 900 and then 100 millivolts at 100 millivolts per second. And then I can select the mechanism. And in this case, I know that it's a simple one electron transfer reaction. It's an oxidation reaction. In this case, A was going to be plus an electron. I started the potential here, positive potential, swept it, got some oxidation current, and then on the reverse, I was reducing it. So I'm going to eyeball it. The E naught is around, say, 400 millivolts. Let's just call the rate constant 1. This was this was ferrocene. Of course, I didn't have a perfectly super perfect electrode, but 0.5. But it has a very fast rate constant. I'm going to call the diffusion coefficient for 5. 1 times 10 to the minus 5. Maybe it's 1 times 10 to the minus 6. And let's just say I had 1 millimolar, and I have the same conditions here, except I don't have any of it. So with this, I can simulate the voltammogram. And from here, you can start to see, oh, the voltammogram I'm getting is so much larger than my experimental voltammogram. So there are a couple things that this can be due to. This could be due to just like the electrode area. Let me just try simulating it. Oh, now I made it way too small. But while I don't have the ability to fit the data exactly, you would of course want to use experimental parameters. While I don't have like a button that helps me fit the data exactly, there are ways where you can adjust parameters. If you know the solution resistance, some double layer capacitance, you will be able to at least fit. You can adjust the simulated parameters to match your CV results. So we're hoping to add fitting in the future. So the answer to your question is like, no, we don't have a fit per se, but you do have the ability to overlay experimental data and then simulate a voltammogram on top of that. And that's just a 1 electron transfer reaction, but there are a variety of different electron transfer chemical step reactions that you can simulate the scan rate, things of that nature. So hopefully that shows you what we're capable of, or what our software is capable of, when it comes to fitting experimental CV data to simulation. And I would just show you just one quick thing, because I did mention this during my webinar this past week, was that we're hosting a special on Aftermath Live software, where if you're interested in this offer, it's 67% off the annual research edition, which is normally $1,000, but you would actually just pay $330 for an entire year license of like all the best and greatest features that our software has to offer. Similarly, we also have, if you just want to try Aftermath Live out, it's 40% off the first month of the basic edition. Normally $35. Instead, you'd pay $21. So this offer only lasts until October 31st. So you have a little over a month to think about it, decide to make a decision. But something that's normally $1,000, and we're giving a very steep discount, if you will, for it, because we know that the funding situation is a little tentative now, and I know that for a lot of you who are trying to use Aftermath Live for research purposes, but also for like learning purposes, Neil and I use Aftermath Live a lot. Just like Neil, what happens when, if the rate constant is super slow and I have like fast like chemical steps, or what does the voltammogram look like? Well,
I don't know, Alex. You should
I
simulate
should
it.
simulate it. It's like literally every time you guys ask certain questions, we always turn to Aftermath Live when it comes to how do voltammograms look. We always go to this software to kind of look at it and see why it happens. So if you're interested, my email is right here. You can also contact pinewire@pineresearch.com. And then I'll be able to send you, if you're interested, the discount code for the Research and Basic Edition if you are interested. So I just wanted to share that while we're talking about Aftermath Live.
Very good.
Yes.
Yes, take advantage of that because that's not going to last forever. Trust me.
Yeah. Yes.
All right. TT is back with a good question. For GCD, how to know whether the sharp line in the discharge is IR drop or not? If it is an IR drop, is it necessary to be compensated? No, you're not going to compensate IR drop and galvanostatic charge discharge. But most probably it is IR drop, but I just want to clarify. So for example, if you have voltage versus, let's just say, capacity, it's time, it's capacity, it's the same thing. For those who don't know batteries, that might not make sense. That T is like the longest horizontal part of the T.
It's good.
I'm going with it. You're
going with it.
Yeah.
It's good.
Okay. So if, for example, what you're referring to, if this is the V upper limit and this is the V lower limit, okay? And let's say, so this is 100% state of charge, right? And this is 0% state of charge. So let me just clarify one thing, right? If what you're referring to, for example, is that when you start let's say it's at 100% state of charge and you start discharging, right? Normally what you'll have is something like this, right? That will be your discharge or whatever. If you are referring to this as the drop, that's not the IR drop. That is not what that is. That's just part of the discharge curve, right? This is like kinetic region. There's similar kinds of terminology or phenomena we talk about with fuel cells and polarization curves and stuff. We sort of have like the kinetic region, and then we have the mass transport limit region. Generally speaking, with batteries, we're just kind of concerned about this part because this is where there's a relatively linear relationship between voltage and state of charge, or voltage and capacity. And so that's what we're kind of looking for, is this long enough plateau that gives us our good time spent, for charging and discharging. It gives our good capacity, everything like that. Okay. That's not IR drop. No, that's not what that is. However, if what you're referring to, for example, is, let's just take this on like a time, right? And this is voltage. All right. And let's say what we have are two steps, right? We have an OCV, we're doing OCV, and then we have a constant current discharge. Okay. And the time is here. And so if my OCV is just kicking around like this, and then as soon as I start my discharge, I'm going to get something like that. That is the IR drop. Okay. So, and similarly, in a different situation, let's say I have, a different program. So I'll draw it down here a bit. Let's say this is constant current, and then I have OCV here. Okay. And so I'm charging it up to whatever. And then when I release it, my OCV will settle out below where it ended, right? That right there is also the IR drop. Okay. The most common way to think about it is it's the difference between when my current is on and when it's off. The difference between the OCV measurement and the IR and the voltage measured during charge or discharge. Okay. That is directly the IR drop. Okay. And the way you can convince yourself if that's true is do different C rates. So for example, if you want to know, because IR drop, I times R, well, the resistance is, let's assume it's the same, right? So if you have a 1 amp hour battery and you have 1 ohm, I'll just use like the easiest numbers ever, right? 1 amp hour battery. Well, if I charge at 1 C, that means I'm applying 1 amp, right? So 1 amp I times R, 1 ohm, is 1 volt. So I mean, that's crazy. That's a lot. Forget about how crazy it would be to have 1 volt difference from what you want. Just pretend the numbers aren't that big of a deal. But that's what you would get, right? Okay, well, if I instead charge at C/10, then I'm applying 100 milliamps, right? What's my IR drop now? Times 1 ohm, it's 100 millivolts. So it's still really high, but that's 10 times less, right? So if you could say, well, one way to see if my drop in my voltage, for example, is related to IR drop is if I have a 1C versus a C/10 step between, so this is time and this is voltage, okay? And we have OCV to constant current. Let's just say discharge, right? So if my OCV is like this, and I do a 1C discharge, it's going to be like down here, right? And the C/10 is going to be like this because my IR drop is lower, right? So that's one way to sort of convince yourself. Do different C rates and see how the difference is. Now, the charge discharge capability will also be different because the time it takes to discharge T/10 is going to take a lot longer, and the 1C is only going to take 1 hour. It's quicker. Part of that's because the IR drop eats up some of your voltage. Part of it's because just faster charge and discharge means it gets finished charging and discharging sooner. But the IR drop is really mainly observed with that difference between OCV when your current is on and when your current is off. That's when the IR drop is really manifest. Okay, so I hope that's kind of clear.
Yeah. TT had a comment.
Case.
He says, the second case after the plateau, it started to discharge with a steep discharge line, then it continued a gradual decay normally.
Yeah.
Yep.
Yeah.
Yeah.
So it's
IR
the on-off current difference is where you're going to see that IR drop. And so if you want to minimize the IR drop, people either charge very slowly, discharge slowly. When I is smaller, IR is smaller. And that's another reason why people, for example, they add the constant voltage step. The theory is that you top off your charge, right? You charge up at like 1C, and then as soon as you get to like 4 volts, your upper limit or whatever, you release the current and it sags to 3.9 volts. And you're like, well, what gives? I want to go to 4. And it's like, well, it did, but IR drop was eating up some of the voltage, so it kind of sagged, didn't make it, didn't really make it, kind of didn't make it there. So then you could hold the voltage at 4 volts and let the current decay. And you're like topping off the current, you're topping off the charge essentially. There are some studies where I've seen where people show that doesn't do anything. Like it doesn't actually improve the battery. The idea was like, oh, that'll improve my battery longevity because it's like, I'm technically charging more. It's like filling up your gas tank, like squeezing the gas pump a little extra time to add a few extra drops. Like that's the idea, right? But whether it actually has a tangible benefit to the battery is, at least as far as I can tell, it's suspect. But people still do it. So,
yeah, TT has a further comment. He says that his lab mate insists that it, being the IR drop, will mess up the capacitance calculations and wants to compensate for it.
How are you calculating capacitance through charge discharge? Capacitance calculations are probably calculated through impedance, in which case the IR drop is irrelevant.
Maybe he means capacity.
If you mean capacity, that is incorrect. No, I shouldn't say it that way. Look, you can't get away from the fact that you have an IR drop. There is some resistance in the battery. Now, the good news is that normally batteries have very low resistances, which is why the IR drop isn't too bad. It'll be some amount of millivolts, but you can't compensate for it. I'm trying to think how to So, okay. So let me put it this way. The way that you would think about compensating for it, right? So the idea from the area under the discharge curve,
So he's looking at what voltage over.
you're integrating voltage over time. That's like scan rate. That's not capacitance. I'm not sure how you're getting capacitance from that. So
What
current,
if it's voltage over? Oh, yeah. Okay.
It's voltage. The area under the discharge curve is voltage over
Versus-
current. So if the area under that is the
Yeah,
multiplicative. That's either
yeah.
voltage times time, actually.
Yeah.
Which isn't anything.
What if it was capacity? Voltage times capacity?
Voltage times capacity.
Is that also?
So capacity is
Coulombs.
It's coulombs.
It's
So
coulombs,
what's
yeah,
volt
amp
times a
hours.
coulomb? Is that a farad?
Well, his lab mate is suggesting. I think while there's the detail of the calculation, I'm also thinking about conceptually.
It's coulomb over a volt.
Coulomb over a volt is
a farad. Yeah, I don't know what the area under the discharge curve means anything.
Well, then maybe
as far as capacitance, capacity, like capacitance is farads, right?
Yes.
Capacity is coulombs, technically. Like it's amp hours, but it's coulombs, right?
Yeah.
Amp hour is just coulombs. Let's just fundamental unit.
Yeah.
So if you have a plot, for instance.
Oh, but yeah, and he has, but just like a capacitor, you have charge in coulombs is equal to capacitance times the voltage. If you divide the charge in amp hours divided by
charge is equal to capacitance times voltage
of a capacitor, like the charge of a capacitor is equal to the capacitance times the voltage.
Q equals C times V.
Yeah.
Right, because
that's
I is C times nu, right?
Yeah.
Right. So on a battery plot, you have like Q here, and you have V here.
So he is getting
No, the area under this curve.
The area under this curve.
The area under this curve is V times Q. Technically, that's what this.
That's what
area.
That's what area is.
V times Q is not C.
So then it's like
C is equal to Q. C is equal to Q over V.
Yeah.
So in other words, I don't know what you're doing precisely, TT, but the area under the curve might have meaning, but it's not directly capacitance.
Oh, wait.
There's something.
Right. We're getting a little bit more. We're getting some more information from TT. He's saying for battery type supercapacitors, we calculate it from the integral of the voltage change by time. So we use area under the discharge curve. So he's looking at voltage versus time.
So if we have voltage versus time, it's the same curve because the area under here again would be V times time.
Yeah. So voltage times time.
I don't know what voltage times time really is.
I'm trying to think if there's a relationship between those. That's obvious in my mind.
Voltage times time is not farads. Farad is a second per ohm. It's also a coulomb per volt.
Yeah.
I think I would need to have like a paper, TT, to know precisely where this calculation you're doing is coming from. There might be a way you're extracting.
Oh, wait.
C is equal to current density. Oh, so you're doing current density area under the discharge curve. So, okay. So if you're doing current versus time, then you're getting by discharge curve, I'm assuming voltage versus time or voltage. He might be talking about a different kind of discharge curve. Maybe he's talking about a current discharge curve.
Yeah.
Something like that. But current density times area under the discharge curve over 2 OPW squared. I'm not sure.
But so there's that. But there's the fundamental question, which is when you have IR drop, that entire discharge curve shifts. It shifts down.
Yes.
It shifts down a little bit. So his lab mate is saying that
you would want to compensate.
You want to compensate for that.
So the calculation aside, I might need to look this up and kind of understand precisely what this calculation is, because I don't think I exactly know how you're calculating. But here's the point. All right.
Yeah.
So if I have an IR drop, let's say if I had zero, if IR was zero, right?
Mm-hmm.
IR was zero, I would have this perfect, like let's just draw these out so we can kind of visualize what we would have in a perfect world. We would start here, and we would have that, right?
Mhm.
Now, when IR is not 0, right? Fine. What we're going to have is it's going to start, let's just say it's something like this.
Yeah.
Right.
It's like exactly the same, but shifted down.
Right.
Just a little
At all
bit.
points, it's down.
At all points,
Now,
it's down.
your point is like, hey, my capacity is decreased by a little bit, so I want to compensate for that. Okay, think about what compensation means. Now, in a 3 electrode, I won't talk about it too heavily here. I know it's like get into a whole ball of wax of like the IR compensation with a potentiostat circuitry or whatever. Suffice it to say that when a potentiostat compensates for IR drop when it comes to something like CV, what it's doing is it's boosting the voltage artificially so that some of it gets eaten up by the IR drop, and then at your working electrode, it gets exactly what you're after. Okay. For this kind of test, it's normally done galvanostatically. I assume you're doing it galvanostatically.
Yeah.
What would you do, right? To do this, you would boost the current. You would boost the current to be higher, so that it would end up here, right? So it's like you would boost the current to be like up here, so that whatever gets eaten up settles itself down. So like you would boost the current higher, right, in it without IR, and so that the IR that gets eaten up, it goes down here. But what does that actually mean? Well, that means that if I'm trying to do like 1C, well, I'm actually doing like 1.4C. I'm actually putting more current into it.
Yeah.
Like you're actually not charging it at the rate that you think you are. You're charging it faster. I know you're saying that some of it's getting eaten up, but the reality is that that amount of current is going through your cell. Like that's not ideal. Like you're not actually charging it at the, like you could say that you would end up with the black line, but if what you're looking for is you want the black line for a 1C charge, well, you're going to get the black line for 1.4C. Like you're not getting what you think you're getting. Like with CV and a compensation, you're getting the voltammogram at 100 millivolts per second for the voltage that you want at your working electrode. Like that's what it's doing.
Let's see. So get into some more details. So like my lab mate thinks that this drop takes up from the area under the curve. Calculations will be less than what it actually is. Actually, we all think it will significantly not, but I can't convince her. So here, this is, so if I may, my 2 cents is that the discharge curve, the charge that's calculated is the charge. So, this is some stuff I actually learned recently this summer. So there are actually several things in charging, at least for a battery. I'm just talking about a battery. Maybe it's different for a battery type supercapacitor, but there are actually a bunch of things in your electrochemical system that lower the the kind of theoretical maximum, sort of say, of your discharge curve. So IR drop is one thing, but there's also losses due to kinetics. Like there's also losses due to mass transport. You know, there are other things that, like, from a theoretical perspective, all minimize or change what your discharge curve should theoretically look like if there were no other issues. So so I'm with Neil on the sense that, like, what you actually measure is the actual amount of charge that is built up, and that, like, you wouldn't want to, like, calculate the IR, like, you wouldn't want to add IR calculations to it because you wouldn't get the actual capacity. And you know, there are other things like, oh, like the kinetics of the battery are actually, you know, not as fast, and so there's a loss due to kinetics. This was actually something that blew my mind. It's the Butler-Volmer equation just turned on its head. It's like, you set the current and you observe an exponential loss due to the voltage change. So there, even, you know, to a certain degree, a real charge discharge curve with that had no limitations would follow the Nernst equation exactly. But because of real limitations like IR drop, mass transport, and kinetics, you get this real curve. It's just those other losses manifest themselves differently.
Yeah.
So,
but I think the other point that I make here is that, so for example, you're arguing with your lab mate, she apparently thinks that the losses, for example, are going to impact your results. You don't think it's that severe. Here's what I would say. Whoever is right, it depends on the magnitude of the IR drop. So in some cases, if, like, for example, if you're doing a very slow discharge or charge, then you're probably right. The small amount of current that you're charging or discharging with means the IR is small, and because the IR is small, its losses are going to not impact the surface area, the calculations at all, right? But if your charge is fast, then it will. However, regardless of who's right about whether it impacts the surface areas that you get or not is actually irrelevant, because what you're getting is real, like you just said. There is no way to compensate for it without eliminating what you're trying to get. So again, I know it's hard to talk through this if you're like not in our heads with like the potentiostat diagram and how review our video or webinar on how potentiostat works and how IR compensation works, right? Like with a 3 electrode system, you have a working electrode, a counter electrode, and a reference electrode, right? The IR drop is taking away voltage, just like this is, that the working electrode is experiencing, okay? It's not taking away the current though. The current is what it is. So here's the key, right? It's taking away some of the voltage. You lose some voltage. That's the IR drop. So what the potentiostat does when you compensate in something like CV in a 3 electrode system in solution is that it bumps the voltage applied to the counter electrode and therefore to the working electrode, so that what gets eaten up is by the IR drop, and then at the working electrode, you get the voltage you're after. When you're doing charge discharge, you're not after voltage. You're after a current. You care about the current you're putting in because that's the rate at which you're charging. So if you just fundamentally change the current so that the voltage lines up with where you think it should be, well, now you're not charging at the same rate. Like you're trying to get the charging characteristics for a certain rate. That's what charging is all about. And if you're not, then I'm not sure what you're charging. Like if you're just randomly charging it up and down, then maybe that doesn't matter. But like, you generally have to know the rate at which you're charging. 1C, C over 2, C over 10, 10C, whatever. You're charging it up at a certain rate. Well, if you add or subtract to or from that rate to make your voltage overcome or something like that, well, first of all, you're not getting rid of the IR drop, because let's say you bump the current so that it the voltage will drop down to that black line actually now you just have higher IR drop because you're adding more current. And so now it's like, well, if you want to overcome that, you have to keep it going. Like you'll just end an endless feedback loop of like adding more current to overcome, theoretically, like to get somewhere. But all you're doing is just increasing your IR drop by increasing your current. Like this exercise doesn't work. And anyway, the IR drop and the losses from IR or kinetics or whatever else are part of your discharge curve. They just are.
Mm-hmm.
They're part of it. And so the thing I would say is that, again, if the IR drop is significant, it might impact your area under the curve, which again, I'd have to look this up a little more. I'm clearly not understanding precisely the calculation you're doing to get capacitance. But what I would say is that if my intuition tells me that it's not, for the reasons I tried to explain, I know maybe it's not clear, it's a little tricky, but it isn't really appropriate or possible, in my estimation, to compensate for the IR drop in a battery context. And so what that means is that if you're calculating capacitance from an area under a curve that is impacted by IR drop, you ought not to do so. Because that's why impedance is useful. You can deconvolute resistances, IR drops, charge transfer resistances, and capacitances. It doesn't matter if there's IR drop or charge transfer resistance or anything else when you do impedance on your battery, because you can fit specifically for each of those components. You can fit and get a capacitance or a CPE value separately. But if your requirement is I need the area under a curve, and I'm assuming that curve is just the capacitive process, but it isn't, then you're going to have error. You will have error. So I do think it's possible that your colleague, I guess in this case, ultimately is correct. That,
wait a minute. We ended with like, oh, she's correct.
yeah, well, it's possible. If she's concerned that this is affecting the measurements and there is a significant impact from it, and you're calculating it from an area under a curve, then yes, I think it is possible. It could be erroneous.
I still think like you know it like it is what it is. Like what you actually measure is the thing, and whether the IR drop is causing that error, it's like, well, but just as you said, it's also like when you compensate, you're getting a different result.
It's a different result. It's a different
result.
Scan rate. It's everything. Yeah. No, it's true.
Yeah.
Maybe it doesn't matter because that is the result. I guess it's just more like what you're not doing in this is deconvoluting in any way the impacts from these two phenomena, capacitance and IR drop.
Yeah.
They're contained within the same data, whereas impedance deconvolutes from them.
So that's actually his next question, which is like, which you kind of mentioned a little bit, like how do you use EIS to determine the capacitance?
Yes.
There are a bunch of other questions. I don't know if you have time, but like you would, in short, you would do EIS of your battery, you know, whatever state of charge it is or state of health.
Mhm.
And then you get some semicircles. You would need to determine which semicircle is associated with your anode, with your cathode,
Yeah.
SEI formation. But when you fit the, you would need to determine how would you model that particular EIS circuit based on your battery's construction. And then you would do circuit fitting. And because part of your circuit fit contains capacitors for that particular, you know, element, you could then, you know, as you fit it and you get a good value, that you know has a good, you know, chi-squared and is valid, then chi-squared, then you can use the capacitance, that impedance, like it spits out the parameter value for you. So that's the way you would determine what the capacitance is, which is, I know, it's a little hand waving. If we have time, we can talk more
if
about
you
it.
need like a specific example, I might have some data I could show, but we'll move on for now because we've kind of been in here for a while.
Yeah.
We'll back up here. I think Gaurav had a kind of a general question.
Yes.
I'm not really sure
What is
how to answer this. What is an electrochemical cell? I mean,
well,
it's very general.
Yeah, so an electrochemical cell, for something to be considered an first off, I think that there's two things to kind of define. There's, I would say, the academic definition of an electrochemical cell from a textbook, which is, you know, an anode and a cathode, just like something that undergoes like a reduction reaction and something that undergoes an oxidation reaction, and they're connected to each other in some way. Then there is the practical electrochemical cell of like a glass, you know, a glass beaker, sort of say, with like electrodes, and then you know, you hook it up to a potentiostat. And there's that electrochemical cell, and that's glass or PTFE or some kind of object that holds. It can literally be any object that holds your electrodes, that, and maybe has ports for degassing, or you may change the temperature. It could be a jacketed cell. There's that type of, quote, electrochemical cell. So so those are kind of the two things. I think I think maybe you're asking a little bit more about the academic definition, which is to say it is, you know, two sides of the electrochemical reaction, the oxidation and the reduction reaction, contained in a device, and whatever that device is the electrochemical cell. So whether it's glass with an anode, a cathode, or working electrode and a counter electrode, maybe it has a reference electrode, or it's a membrane cell, a fuel cell, a battery, a supercapacitor, all of those devices have a positive and a negative side to them where for current to flow. And so that is the basis of any kind of electrochemical cell. It has to have those two things. You can't just have one and not the other. Although we recently found a LinkedIn article that had like, we have a battery that doesn't have an anode and it's great. And I'm like,
and it's a lie.
Something's wrong.
It's a
Wait,
lie.
This seems weird. I don't, anyway.
I
digress.
It's a total lie.
But hopefully, Gaurav, that maybe that answers your question. I think that's what you're asking. But if you have further clarification, let us know.
Yes. Cinnamon Shy asked a question which was on the heels of my Warburg tirade. How to distinguish whether it is a Warburg short or another semicircle? I saw a Nyquist plot and I couldn't determine whether it was two semicircles or one semicircle and a Warburg short. It is tricky, admittedly. Here's some just visuals for you. So for example, I have a circuit, and it's right here with a RC and then a Warburg short. Okay. Here's what I'll sort of point out. Whether it is another RQ or RC or a Warburg short generally depends on whether or not there's a 45-degree observable section right here between the two, right? Now, right here, it's like, well, is that a 45-degree section or is that just the start of a new semicircle? Kind of looks like both, right? There will be cases where for sure it's almost indistinguishable. It's like, you could probably fit that with just two semicircles, right? And to my point during my slides, I mentioned that the sort of pseudo, if you will, resistance of a Warburg short is W times B. So what you might be able to do, for instance, is in some cases like this, you have a situation where, okay, I can multiply W times B, and then whatever that number is, this is, 13,000 times 0.07, whatever that number is, a number of ohms, right? You can see this is even just the units here. This is ohms per square root second, and this is square root second. So you could imagine when I multiply these together, I get ohms. Well, if I think this is if I fit this with a Warburg short and it looks like, well, I could just fit a RC, then I could start with an R that's equivalent to 13,000 whatever times 0.07. That would be the equivalent R, and add a C to, add a C in parallel. So visually, it's like there's ambiguity. Now, where it becomes less ambiguous has to do with the ratio of the W and the C value. So for example, when I make these much more different, you see that this kind of dips down, right? You see that this really kind of like dips here. When there's a big difference in magnitude between the Warburg part and the RC or RQ part, you can more clearly see the differences. So the first one's very clearly a semicircle. The second one, this semicircle right here, and the second one very clearly. Oh well, I can see that there's definitely some lagging thing here. I can make this more extreme by adjusting the B, for instance. There will be times where, for instance, it's very clear because you're looking for that 45-degree section. If the answer ultimately will likely come down to something like what you know about your system, right? If you do suspect that there's a porous boundary of some kind with a fixed boundary length, and it's like on the edge, it's like, oh, like this could be interpreted like it could be or not. You can just fit with the Warburg short anyway. And if it devolves, let's just say, to something that looks like two semicircles anyway, well, then fine. You have an effective resistance right here anyway. You could also just do two different circuits. If it looks like this, you could do the Warburg short. You could say, well, this could reflect a Warburg short with this value of W, or I could fit two RCs and present both sets of data as part of your analysis. But again, mainly the thing you're looking for is where you have this kind of magnitude difference between the Warburg parameters and the capacitance, and particularly if your B value is large, it will really more obviously make this 45-degree section at the beginning of the Warburg short visible or not. Okay, so that's kind of the main key is, again, the ratio of those two, and then how big the B is, so whether this 45-degree section is visible. And again, I think that the key is if you can tell with your system something knowledgeable, like I definitely have pores for sure, then fitting the Warburg short is probably a good idea, because you're going to be covering, the situation that's going on in your real system more accurately.
All right, very good. All right, as we get through these, I think Ahmed is next. Ahmed says, "Hi, I have some questions about lithium solid batteries. How does the lithium transport number in the electrolyte affect battery performance, charge discharge kinetics, or dendrite formation?"
So I think that what it means basically like is so lithium transport number is like the amount of charge carried by the lithium, which is
Yeah,
basically just like how concentrated your electrolyte is, basically. I might be oversimplifying this, but it's like if you have 1 molar LiPF6 or like half a molar or 0.1 molar, you would, or if you use lithium with an anion like Li, ClO4 versus LiPF6 versus Li, I don't know, whatever the conjugate anion is, the amount of like the mobility or the amount of charge of the lithium compared to the percentage wise or something of like the how easy the lithium plus moves compared to the anions or something like that will change basically. Very generally, I don't have a ton of knowledge of that specifically, like calculating that number. There's like the Bruce
yeah,
Vincent method is a thing. We've talked about that. I've gone over that in this live stream before. In previous episodes, I've talked about the Bruce Vincent method. It's not something that I'm like extremely familiar with, but I did look it up and kind of try to give a brief explanation as best I could on that method as it relates to transference numbers. But very, very generally, what I can say is that I believe something like lower concentrations of lithium and not having a like high enough lithium concentration in your electrolyte will decrease your performance and increase dendrite formation likelihood. It's usually why you want to take that fact. Most people take that out of the equation by using a very concentrated lithium salt, so as to have plenty of lithium ions present flooded everywhere in your battery at all times. So you're not sort of limited, because if you're limited, you might end up with sort of this preferential formation on the anode or the cathode during charge discharge that can form a dendrite, things like that. When there's ubiquity of lithium ions everywhere, it's less of a problem. And you don't. I'm not sure. Probably affects kinetics. Isn't like it's more like it'll affect the performance, because the mass transport will be like you'll be waiting for lithium ions to reach the surface if there's not enough of them, something like that, right? Kinetics is what it is. Like that's independent of the diffusion. But if you're waiting for the random motion of lithium ions to make its way to the surface, and there's only like 12 of them as opposed to a million of them, it's going to take, your performance will be poor, something like that.
yeah. I vaguely remember. I remember listening. Paul Cole was talking a little bit about this. It's like because the current is carried, so it's like for every it's like for every positive charge, lithium ion, you have to have a negative charge,
Mhm.
and how much of the current that moves through the system is carried by the charge. And I remember Paul mentioning that like the transport number represents like a power issue at the end of the day, because um, if it's like you can add a ton of like lithium to your system, but if it turns out that lithium only has a transport number of like 60 or something, only 60% of your lithium, it's because your lithium is both the electrolyte, it's also the thing that is moving.
Yeah. It's the
It's
reagent
the
or whatever. Yeah.
reagent too. So by definition, that creates these limitations, sort of say. So so I think I remember him saying, and he had this like very simple equation that I don't remember, but that was kind of the argument that like you want to pick an electrolyte and lithium in such a way to maximize the transport number of lithium, because that limits what percentage of the lithium actually ends up going into the current, which is your reagent that keeps the rest of the electrochemical cell charge balanced.
It's like twofold.
It's like twofold.
Yeah.
And that can limit the current. It's like, oh, you have so many moles of lithium in your battery and you can only use half of it. So the current you're going to get is cut in half. Well, and with the voltage of the battery, and most, I think, engineers are looking at, how much power can I get? it's like your power is always going to be cut in half, or it's
Yeah.
going to be 60%, just because you can't get access to all the lithium. That's I think that's what he said. I have to review the notes, but that was the other thing about, like, that's the only thing I remember about, like, lithium transport number from Paul. So
Well, I think it's a good point in general, and
Yeah.
it also even more highlights the idea that you want to maximize the amount of lithium plus in a battery, for instance, because it not only is the diffusional,
reagent.
whatever, but it's also the reagent, you know what I mean?
Yeah,
So
yeah,
it's twofold. It's like
exactly,
you
yeah.
want to have as minimal losses from diffusion or having enough electrolyte present and all of that, but also have enough to be able to intercalate and move around and react, because it's the lithium plus is everything.
Yeah.
So that makes
Exactly.
sense. Okay. Parallax says, I'm going to start electrochemistry in grade 12. Where are you going to school that you're doing electrochemistry in grade 12? Good for you. Very soon. Any tips on how to start, or some notices or anything, as I am very new to this? The Nernst equation.
Watch all of our videos.
Yeah. Yes.
To a
Watch
certain
all of our
degree.
videos on our YouTube channel. We have a lot of videos on a lot of the basics of electrochemistry. Things like cyclical voltammetry, impedance. I guess that's not basics. That's pretty.
Yes, even
somewhat-
cyclical temperature in the EIS is very
they could be
advanced.
pretty advanced, but like they're like the most common techniques. For instance, chronoamperometry. You have videos on that. We have a lot of videos, a lot of these live streams. Just watch all 100 some odd hours, 200 hours of our live stream over the years. No, honestly, the simplest things, like electrochemistry 101, is like learn the definitions of like potential and current, right? As simple as they can be. Don't ask this guy what potential is. He'll talk to you for like 7 hours.
It's a chapter in class 12 in India. Oh, interesting.
Oh, wow.
Okay, that's what Parallax is saying.
Interesting.
It's a class.
It's a chapter in class as a senior in high school.
Wow.
That's pretty cool. I mean, learning electrochemistry before college level is relatively rare. So good for you.
Or maybe we're just getting super old.
We are old.
We are old.
That is true. That's not a maybe. That's a
that's a true statement.
But like potential and current, all electrochemistry fundamentally involves 3 variables only: time, potential, and current. I know we're talking about capacitance and resistance and all these. Those are like secondary things. Fundamentally, electrochemistry involves doing something to the potential over time and measuring the current, or doing something to the current over time and measuring the potential. That's like every electrochemistry thing you'll ever do. Now, there's 1.5 million ways to do all of those things. There's 2.5 million ways to analyze it once you've done it. And there's 3.5 million ways to figure out what potential and current really actually are and what a potentiostat's actually doing. It gets complicated, but very on the most basic fundamental level, it's those 3 variables: potential, current, and time. So focus on those. And then the most basic equations that describe how potential and current and time do stuff in an electrochemical experiment as a result of other parameters like temperature and concentration and all these other things. You're looking at the Nernst equation, the Butler-Volmer equation, the Cottrell equation. Some of these describe thermodynamics. Some of these describe kinetics. Some of these describe mass transport. But those are some of the most fundamental equations that you'll want to just get familiar with as far as describing how potential, current, and time change, basically. I don't know. Do you have anything else to add? That's a very
no. It's kind of hard, because I feel like in India, when they teach electrochemistry, it really reminds me of like general chemistry. Like you're going to relate the Nernst equation to the potential is related to the Gibbs free energy, so it's ultimately looking back at like thermodynamics. Often is the case. But yeah, it's like I'm not 100% sure what stuff in particular. Like, it's a class, but how, like, if it's a whole class in high school on electrochemistry, like I know a lot of material that they could cover, but I'm also like, I don't know what they would actually focus on. Like, you could focus on so much stuff. Like, you could focus just on DC voltammetry. There wouldn't be any impedance. You could focus on heterogeneous you could focus on catalysis. You could focus on corrosion. you could literally just focus on pore bay diagrams. You like legit, you could just look at pore bay diagrams and look at changes in oxidation state as a function of the pH. Because there's so many, you just draw pore bay diagrams until you're, blue in the face.
I just looked them up.
Yeah.
I don't draw them. I look them up because I'm
Yeah.
an engineer. I want to know what it is. Oh, cool. That's what it is. Cool.
Yeah.
I multiply it by 12 and I'm good.
Yeah. Yeah. So, yeah. I don't know. Hopefully that's helpful.
Pop back in on these live streams as you
Yeah.
start going through and ask questions. We don't really
That's
do
the best advice.
We don't do, for example, like answer your homework questions. It's not really our purpose here. Like, oh, tell me what the Gibbs free energy is for a system that has a delta H of this and a T and an S of this. No, that's not
5 millimole. Yeah.
It's not really. We're not here to be homework solvers per se, but I'm happy to help try to understand and explain these concepts as you're learning them. We're here every Friday, most Fridays. Well, when we're here.
Yeah, when we're here.
But which has been sporadic, but I think we're mostly calmed down at this point.
Yeah. Yeah.
Okay. Well, good luck to you, Parallax. Hopefully your class goes well, and we're happy to try to be a resource for you. TT kind of followed up, I guess, just saying that they're doing some titanium phosphate oxide TiP 207. It's like almost looks like a power core, but it's not quite. Anyway, cool. Well, good luck. Yeah, I guess hopefully we kind of talked that to death. I think we'll kind of leave that there. Constance has a question. Does EIS affect the battery behavior? I did an EIS after 200 cycles. Then I put it back, but I noticed its behavior became worse. If so, when can I apply EIS so that it won't affect the behavior? All right. So as a general rule, EIS should not affect the behavior. If it does, something has probably gone wrong. So impedance is sort of by definition non-invasive, which means it's not supposed to really adjust the steady state, right? It requires linearity, causality, and stability. And so if you have caused or made your system unstable as a result of your impedance, you didn't maybe do it right, which means probably that your amplitude was too large, or your frequency was so small and slow that over the course of the very slow frequencies, you are actually appreciably charging or discharging your cell, which is not ideal. Okay. So it's possible that you need to tamp down the amplitude or probably you're doing it at OCP. But most of the time you want to do, the rule of thumb I usually like to give for a battery for doing impedance, it's usually done at a no, at it's not really OCB because it's galvanostatically, but you're usually doing galvanostatic impedance with a zero baseline. So you're not applying any current while you're doing it. So it's not charging or discharging. It's just it's at open, open conditions. And start with an amplitude of about C over 100 and then step it up slowly from there until you get decent results. Most probably at C over 100, your results will be kind of garbage, like noise, which is okay, because you almost certainly won't damage your cell by doing impedance at very, very low amplitudes. It's like you're not perturbing anything. You're not even doing anything. So that's fine. And so increase it slightly until you start getting decent looking Lissajous plots, semicircles, ovals, I guess, in your Lissajous plot. If you have a potentiostat that shows you Lissajous plots, that would be ideal. Slowly increase your amplitude until you get results, but not higher, because it's possible that what you've done is do, like I said, impedance in a way that perturbed your system. You don't want to do that. Now, it's possible something else is going on with your battery that's entirely separate, and the EIS is coincidental. It's possible that your battery has a leak, a short, self-discharge, something strange is going on, and the fact that you did impedance is just secondary. Your battery behavior got worse. You could just let your battery sit for a bit, do tests, and it got worse. And then you just happen to do impedance, and so you're assuming that the impedance is what made it worse. That may not necessarily be the case. There's a lot of things that can go wrong with batteries, and construction wise and otherwise. So that could be the problem. But do Kramers-Kronig on your impedance results as well, is what I would suggest, because you might find the diagnosis of well, my system isn't stable because I used too high an amplitude. That's causing my system to get perturbed and make my battery worse. And the Kramers-Kronig would show your EIS results were not valid. That's a possibility too.
Okay. Ahmed has a question. His question is, in CV, why does increasing scan rate can turn a slow system into a fast Nernstian one, diffusion limited? Also, why does increasing scan rate increase capacitive current if the maximum potential stays the same? So, a couple things. I don't think your first statement is necessarily true. If a system is slow, like due to kinetics, or maybe due to diffusion, increasing the scan rate doesn't all of a sudden make it better, or make it fast. If it's anything, going to faster scan rates only exacerbates the kinetics of the system. So, for example, I can just show you very simply in our simulation software right here. If I create a if I do a CV, and then if I just do a 1 electron transfer reaction, if I simulate it, this is the heterogeneous rate constant. This rate constant right now is very fast. I'm at 100 millivolts per second. But if I go very slow, let's say 0, 1, if I simulate it, it's sluggish. This is a slow system. The heterogeneous rate constant is slow. But as I go to faster scan rates, it gets worse. The peak separation between these gets worse and worse and worse. So the changing the scan rate does not make a slow system that isn't Nernstian all of a sudden Nernstian. In this case, it actually exacerbates it. It makes it worse. So that's kind of the first thing. And so if I'm missing something with that, please clarify. Oh wait, let's see. I think he said, sorry, I meant okay, I'm sorry. I meant decreasing the scan rate. I think it reduces delta E. Yes. Okay, right. So that's true. As you do, and actually it's the opposite of what I was showing you. If you go from fast scan rates to slow scan rates, you start to the peak separation starts to get better and better. So yeah, you're correct. So your question is, why does that happen? So first, I wouldn't call it so yeah, I don't know, calling it Nernstian is a little odd, but the reason quite simply is that the scan rate changing the voltage and adjusting the speed with which the electron transfer occurs, if you give it more time because the scan rate is slower, the chemical system itself just has enough time to reach, quote, equilibrium. Yes, in a way, reaching a, quote, Nernstian state. So as a result, the peak splitting gets closer and closer to its Nernstian limit, which is 57 millivolts per electron transfer, 57 millivolts divided by n. So so I don't know if that kind of answers why. Like when you go to slower scan rates, it gives it more time for the current to get closer and closer and closer to its ideal system. But if you're going like super fast, by the time it's able to react, it's like, okay, now I have the current, but I'm at such a high over potential, sort of say. And actually, maybe that's probably the best way to describe it. Let me actually pull up the not this. This is the Butler-Volmer equation. Oh, we have one of our caption designs showing. Let's hide this. Yeah. So okay, right. So if we're on the Butler-Volmer equation, for example, this is really the way that it's described and looked at. So you can look at the E minus E naught in the Butler-Volmer equation, and if K0, if K naught, the heterogeneous rate constant, is very slow, non-Nernstian, then for you to get any appreciable current to flow, then the E minus E naught has to be really, really high because it's exponential to get appreciable amounts of current. So it mathematically conforms, if you will, to the Butler-Volmer equation. And that's just to say that you need much higher overpotentials to get an appreciable amount of current, because thermodynamically, the kinetics are very slow. You need to supply more free energy, because the conformation of your molecule is not very likely to happen. So you need to be in a very high energy state. This reduction or oxidation reaction only happens when the potential is sufficiently high. I hope I'm at the right thing. Yeah, is sufficiently high such that you're able to undergo the reduction or oxidation reaction. I hope that kind of makes sense. So the peak splitting follows the Butler-Volmer equation, like almost like to a T, basically. So that explains why it is that as you change the scan rate for slow rate constant systems with slow rate constants, why that delta E starts to change. Now, the other question about why does increasing the scan rate increase the capacitive current? This is, I think, I don't call it my favorite thing, but it's just, I think it's very easy to show that the capacitance, so whenever you have a capacitor, the charge on a capacitor is equal to the capacitance times dV dt. Okay. Oh, sorry, not dV dt. That's I'm jumping ahead of myself. It's equal to it's equal to the voltage.
Yes.
And then when you take the time integral of this, dq dt is equal to C, because the capacitance doesn't change as a function of time, times dV dt. It's just the time derivative. So this is the scan rate or the sweep rate. And then this is just the current. So as we increase or change the scan rate, we necessarily increase the current linearly. And so this is mathematically why we observe this phenomenon. And another way to think about it, if you will, is because you're just like, oh, well, if the voltage isn't changing, then why isn't Q changing? Another way you can think about it is the amount of charge, and the voltage is basically the same. But if you need to, so you know that the charge has to be the same for the amount of current, or sorry, for the amount of voltage, the potential that you're going to keep the capacitor at. And if you're going to reach that amount of charge faster, you have to have a higher current, right? Like, oh, if I'm going to get to this voltage faster via the scan rate, then my current has to increase fast enough to reach that particular amount of charge. So just, and it's nice. It's like super linear, super linear, just based on the capacitance. So that's kind of the conceptual understanding of like, oh, why is it like, oh, the voltage is the same, the charge is the same, so why is it that why is the current increase with capacitance? Well, just has to reach the same same amount in less time, so current's got to go up.
Yep. The dt in the bottom is smaller.
Yeah.
So the number gets bigger.
So the number gets bigger.
Number goes up.
That can also be, you can use that same line of thinking for even just a regular CV experiment. The same amount of charge kind of has to pass, because it's like, well, why does the Randall-Sevcich equation, why do you get increase in current as the scan rate increases? Same amount of charge has to pass for the redox reaction to occur. If you're gonna get to that potential faster, more current has to pass to get to that same amount of charge in a shorter period of time. So
yeah. And just to your point, you might have seen something like this. So this was the Butler-Volmer equation that you showed earlier. Right? Basically, to the effect of the K, the heterogeneous rate constant, for being larger or smaller. If the rate constant is really small, you need a bigger overpotential to get some current out of it, right? So you might have seen something like this in your electrochemistry travels or in a textbook, something like this. This is kind of a very common Butler-Volmer interpretation. So for example, for a large rate constant, for instance, if the x-axis here is overpotential, positively or negatively, basically the current goes exponentially up or down with only a little bit of overpotential, right? But if I have a smaller rate constant, I need a much higher overpotential to start getting that exponential increase. And then of course, if the rate constant's a lot smaller, I need all this overpotential just to get that same level of current that I get at a much lower overpotential if the K is larger. So this kind of Butler-Volmer visual, sometimes it's like turned entirely sideways. It depends. There's both exist, but this is the one that I'm most familiar with. So and I just wanted to kind of show that plot. That's kind of a common representation you might see. Okay. Let's see. I think there's one other question. So we got Ahmed's. There was another question from Constant. Yeah, just about Kramers-Kronig. I think we'll sort of talk about this and then wrap it up here. So I mentioned doing Kramers-Kronig. How does it actually work? Well, that's algorithm. But how can it tell my data isn't valid and what can be invalid in it? Okay, so what is it? Right? It is. What is it actually doing? It's doing this. Technically speaking, what the Kramers-Kronig is doing in software is applying this circuit to your data. It's kind of like a circuit fit. It's not really a circuit fit, so I hesitate to kind of say that, but you can think of it almost like a circuit fit, where it's fitting your data to a resistor, a capacitor, an inductor, and an infinite series of RCs. Okay. The reason for this is that these circuits satisfy the Kramers-Kronig relations mathematically. And so if this fits your data and it fits Kramers-Kronig, then your data fits Kramers-Kronig. It's a transitive property logic is what it is. Okay. This is actually not done via typical circuit fitting though. It's done mathematically. It's a little hard to explain. But effectively what we're doing is a minimization algorithm to see how well this fits. It's actually fitting these expressions is what it is. So these like infinite integrals, it's a bit wonky if math isn't your favorite thing. But what is it testing? It's testing for these three conditions: stability, causality, and linearity. And so as I said, if, for example, your Lissajous plots, they might, this is drifting. It might look like this. They might look like this. Right? They might look kind of strange looking. If your Lissajous plots look like this, it means your amplitude is too large usually. And so it's not linear. It's not stable. So what is it telling you? Well, it's telling you that your system, your amplitude was too large usually. Again, that's usually the reason. And your data was not simple. So what it's doing is it's like charge, discharge, charge, discharge, charge, discharge. It's like changing the state of your battery. Well, technically it's always doing that. It's always oscillating a little between charge and discharge because you're going up and then down and then up and then down. But by a few millivolts or a few, from OCV isn't going to really do much to impact your battery, or at least it shouldn't. And so if you're going up and down by 50 millivolts or something, that might be severely charging or discharging your system with every cycle. And that's not ideal. And that is why it could be, making your subsequent tests worse, as you noted before. So just be careful of that. And the Kramers-Kronig is a good way to kind of quickly check and see. And it, you might find the data shows up, well, it's actually okay. Like the Kramers-Kronig fits really nicely. And then you have to figure something else out. Like it could be some of the other things I said, maybe, but the Kramers-Kronig could quickly tell you, oh, my data is bad. I need to adjust some of my parameters and figure something else out. So,
yeah. Literally this situation right here.
Yes.
You can have a great chi-squared and a great fit, but Kramers-Kronig could say that it's invalid.
Yes, that's right.
It's like we actually got to use
the meme.
we
took
created.
2 hours, but we got it.
I think we used it earlier today. That's okay. We can always switch
It's true.
between
It's true.
memes.
Yeah, we have to get some new ones because we've used them all.
I know.
We need some new memes.
It's easy to go through 4.
Yeah.
It was very quickly.
That's fine. We just keep cycling through
Yeah.
them. It's a nice touch.
It's a
kinda
nice touch,
funny.
and
where
we
you
get to use them.
get to use the green screen.
Yeah, I get to use the green
Which is-
screen.
It's sort of just a blue background, but
Yeah,
it's
yeah.
fine.
We can add some other stuff to it too.
Well, anyway, that's going to do it for us this week, everyone. Thank you again, as always. We appreciate joining us. It's been a few weeks, so we're happy to be back. We'll probably be back next week.
I think so.
think.
I think so.
Yeah.
I don't think I have
Okay.
anything. Yeah.
Well, in any case, we will be back most weeks, hopefully.
Yes.
Back. Everyone's sort of back in university. School's starting up again for most people, I believe, in
Yeah.
most countries. So life gets back to normal, I think.
Mhm.
And I hope everybody has a great weekend and week ahead of you. And we'll see you next time.
Bye.
Bye.